Here's my submission for extra credit 3 towards exam 3 for the spring 2023 semester for linear systems and signals. Here we have a 2-stage Sallen-Key filter. This is the first Sallen-Key filter, and here's the second Sallen-Key filter. Each Sallen-Key filter is second order, and the output of this filter is fed into the input of the second Sallen-Key filter. So when we cascade 2 second order filters, we have a total 4th order low pass filter. The capacitors, I'm using propylene capacitors. I chose my capacitor values, and over here using the MATLAB AFD toolbox, analog filter design toolbox, I created a 2-stage filter. Each stage is a Sallen-Key filter. I input the circuit or the capacitor values I was using. The actual capacitors I used were a 150 picofarad propylene capacitor, and in the second stage it was actually a 1 nanofarad propylene capacitor. But the values which I input here, which you are seeing at the moment, these are the actual values. It was 935 picofarad, which is 0.935 nanofarad. And the first stage, the actual was 150, but the theoretical is 150, but the actual which I put in here is 158. By doing so, we get the value of the other capacitor, which we will need to construct the Sallen-Key stage, and we also get a value of the resistor, which we'll need for the Sallen-Key stage of R1. So, back to the circuit. This is it constructed one more time using the actual values. I'm here in the open lab. Here I have my DC power supply for the operational voltages of the op amps. I'm using LF3556N op amps, and I'm using a plus minus 15 operational voltage. Here you can see the oscilloscope of the gain versus frequency plot. This is currently the F of T is a 10 kilohertz 5 VPP sine wave. And we can see that the Vmax of the channel 1, which is the input or the F of T, the Vmax is about 1.65, 1.64 volts. And the Vmax of the output, somewhere around 1.3, it's bouncing around. These oscilloscope probes are they create some noise in this oscilloscope, as you can see in the image. They're pretty noisy, but these are the only ones available in the open lab, and I've tried to calibrate them as best as possible. But back to the Vmaxes, we can see that it's about 1.64 to a 1.3. If you do 1.60 divided by 1.3, it's about 0.81, which would be 0.81. We could compare this to the 0.707, which should be the gain at the cutoff frequency. The cutoff frequency of this Sallen-Key filter, when we created it in the AFD toolbox, we set it to have a cutoff frequency of 10 kilohertz. So here we can see when we input a 10 kilohertz frequency at that cutoff frequency, we are close to that 0.707, but due to the real world implementation of having actual resistor values, which are not exactly the same as the theoretical generated by the AFD toolbox, same thing with the capacitors, we do have a little bit of variation in this 0.707 at the cutoff frequency, but it's fairly close. And we can see that the signal that passes through this filter is fairly similar. And now I'm gonna adjust the frequency to 20 kilohertz, and what we will see is that the filter will kill the higher frequencies, and the output has been largely attenuated. The Vmax of the input signal is still around 1.6, and the output signal Vmax is about 160 millivolts. So we can see that the gain of the output is far less now.